Right. So, can you see the slide that I'm showing? Classification of control systems.
Yes, ma'am.
Right. So today we are going to do a classification of control systems. Now, as far as classification of control systems is concerned, there is no one unique way of classifying control systems. There are several, criteria based on which the control systems may be classified. So now you can see that, the divisions are given over here. We shall go into each one of them in detail. So control systems may either be static or dynamic, right? So all control systems may be categorized into either of these two categories. That is, they may either be static or be dynamic. Next is that control systems may be classified as linear or non-linear, right? So all systems will either be linear or be non-linear. Similarly, with discrete and continuous, then time invariant and time varying, and lumped parameter and distributed parameter. So we shall go into each of these classifications in details. Right. So first of all, static systems and dynamic systems. Okay. So as far as static systems, there's no need to keep on writing the roll number right now. Okay. So don't, it is, disturbing me. So do not write the roll numbers. I'll call your roll numbers at the end of the class. Then you should respond. Okay. Do not keep on writing because it's a big distraction. Now, as I told you, the systems, all control systems may be classified either as static systems or as dynamic systems. Now, what is the difference between static and dynamic systems? Unfortunately, it cannot show the, okay, let me try once. Let me try the slide show mode. Can you see the, okay, let me see. Can you see the slide that is classification of control systems?
Yes, ma'am.
Yes, ma'am.
The first slide that I showed you, that is visible, or the static and dynamic is visible? Which slide is visible now? I cannot.
Ma'am, classification of control systems and the difference between static system and dynamic systems is visible.
No, okay. So the next slide is visible, not this one. I'll just stop sharing for a moment and then just wait. I'll stop sharing and then actually I want to share the whole thing together so that, okay, basically, let me do this. Okay, I think slide number 56 is visible, is it?
Yes, ma'am.
Yes, ma'am.
56, right. So now, what I want to say is that now you can see the next slide, static systems and dynamic systems, right? So over here, basically, control systems may be categorized either as static systems or as dynamic systems. Now the question is, what makes a system static or dynamic? How will we know that a particular system may be classified as a static system or a dynamic system? Now, you would be familiar with the term dynamic systems because you have already done signals and systems. So can anybody tell me what would be the difference between a static system and a dynamic system? Of course, I showed you that slide earlier, but anyway, from your basic knowledge, can anybody try to tell me what would be the difference between a static system and a dynamic system? What would
Ma'am, in dynamic system, both the transient and steady state behavior is are seen. That means before reaching the steady state behavior, there is some transient period. But in static system, the system reaches its steady state value instantly, and no
Yes.
transient occurs.
Very good. That's a very good, I mean, way of expressing it. Yes, you are absolutely correct. So basically, this side shows the static system. So basically, as you have already mentioned, in a static system, all variables arrive at the steady state almost instantaneously, meaning that say you give a step input and the output you will also see is following a step. So basically, and that would be reached, the output would be reached instantaneously. When you apply the input, the output is reached. If you change the input, the change will be reflected on the output side. That is as far as the static system is concerned, right? Now, on the other hand, from the same point of view, in a dynamic system, all state variables do not arrive at the steady state instantaneously, meaning that all, I mean, responses that you observe will have a transient portion and then they are going to arrive at the steady state, right? So that is, I mean, the basic difference between a static and a dynamic system. Now, just give me a moment. I'll just mute myself a bit. Phone call coming in. Right. So, can you hear me again? Sorry for that. Can you hear me?
Yes, ma'am.
Right. So that is the basic difference. That is, in the dynamic system, there will be a transient portion in the response, and then it is going to arrive. The response is going to arrive at a steady state. Whereas in the static system, all state variables arrive at the steady state instantaneously. That is the basic difference. Now, as far as the mathematical description is concerned, there is a basic difference. Mathematical description means what? In a static system, you would be able to describe a static system mathematically by means of algebraic equations. So you will have, say, x1 plus x2, etc., etc. So basically, the dynamics, or rather the properties or behavior will be described by algebraic equations. On the other hand, in dynamic systems, the system would be described by differential or difference equations. So basically, differential equations would be, used to describe dynamic systems when the system is continuous in nature. On the other hand, difference equations would be used when the system is discrete in nature. So, as far as the mathematical description is concerned as well, there is a difference. Now, as examples of static system and dynamic system, here we have given an electrical system. So you can see that an electrical system with a resistance and an inductance has been taken as an example. So you see that here the equation governing the system is given by, for this particular example, is given by Vt is equal to It into R plus L di dt. So basically, that is the equation governing the dynamic system. So you can see that it is a differential equation, right? And not only that, another thing is that you see that the variables are functions of time. So you see that over here, number one, it's a differential equation. Number two, the variables, that is the current and the voltage, are functions of time. On the other hand, if you look at the a similar example, that is an electrical system which is a static one, you see that this is the equation, meaning that a system with only a resistance would be considered as a static system. So that the equation governing this system is given by V equal to IR. So there is no differential equation. It's not a differential equation. It's purely algebraic in nature. And also, you see that the variables are not functions of time, meaning that the values are going to be reached instantly. They are not going to have a transient portion and the steady state value, right? So you can think of more examples of static and dynamic systems, maybe in the from the mechanical domain or from any other domain. And then, you can classify them into either static or dynamic systems, right? Can anybody tell me an example of a another static system, say from either the electrical domain or the mechanical domain? Static system, I'm saying. Any idea?
Resistive circuit is the example of a static system, a pure
Yes.
resistor.
Yes, that is what I'm showing over here. This example is given. An electrical system with only a pure resistance, that is, the equation is V equal to IR, which is algebraic in nature. So basically, it is a static system. That example already I've told. I don't know whether it was heard because there was a phone call coming in, but that is the example provided over here. It is a static system, correct. Now, I want another example, some other system, which is going to, other system means maybe an electrical one, but not the one with only a pure resistor, which I've already given.
Ma'am?
Yes.
Now, one example can be thought like this way. If you take an aeroplane flying in the atmosphere, there are drags. I mean, getting into a particular velocity, it takes time. But if you take a shuttle which flies in space, then there is no drag force, so it directly reaches its velocity.
No, over there, of course, I mean, it is, you're going to give a force to it, and then it is going to actually, I mean, from the state of rest, it's going to go to the state of motion, and naturally there will be some acceleration, and by means of which the velocity will be changing. So definitely there will be a differential equation governing it. I mean, the motion is going to be governed by a differential equation. You would not be able to express the equation express the motion by an algebraic equation, isn't it?
Okay.
So thanks for attempting, but that is a dynamic system. Anyone else, or any other example that you can think of? The basic criterion is that it should be the equation governing it should be algebraic in nature, in which case automatically your variables will arrive at the steady state instantly. No? Think about, say, for example, if you have an op-amp or pure amplifier, okay, so you give a voltage at the input, you get, what do you get at the output? Another voltage which is multiplied by the amplification factor, just that. So if you just look in, look at that system in terms of the output and input, it is an algebraic relation, isn't it? V0 equal to, or VO equal to some constant, that is amplification factor, multiplied by the input value, input signal, that is, isn't it? So that could be classified as a static system. So there are lots of examples. Think about more examples, right? So dynamic system examples, of course, you are all familiar with the mass spring dashpot system is a dynamic system, isn't it? So over there you have to write down the differential equation governing it in order to describe the motion. So you can think of other examples again, okay. Next, we come to another categorization of control systems, that is either linear or non-linear. Now, as far as linear systems are concerned, linear systems are those systems in which basically you have already studied this, isn't it? So the system would be obeying the principles of superposition and homogeneity. What is superposition? Can anybody tell me? I'm asking you because you are already familiar with this.
Ma'am, if there are more than one inputs acting on a system simultaneously, then the total output or the net output will be the summation of the individual outputs produced by each input.
Very good. Yes, that is superposition. Okay. What is homogeneity?
Homogeneity is the that means if xt is a input and it produces an output of yt, then if we multiply xt with some constant, just like axt will produce an output of ayt. So
yes,
this is the
yes,
homogeneity
very
property.
good. Yes, very good. So those are the two properties, right? Superposition and homogeneity. So I mean, basically all linear systems would be obeying these two principles, that is the principle of superposition and principle of homogeneity, meaning that if you first of all apply multiple inputs, meaning that instead of one input, if you apply two inputs, the output that you had for each individual input, you are going to get if you have applied two inputs, you are going to get the summation of those two outputs, right? And similarly, homogeneity as well, it's correct, what you have said is correct. So if the input signal is multiplied by a certain, say, constant, the output signal also will be multiplied by that same constant. So as far as systems are concerned, all linear systems would be obeying the principles of superposition and homogeneity, right? Now over here you see a plot, but now I would like to draw your attention to this plot. So this plot is the input-output characteristic of a linear system. When I say input-output characteristic, I mean that on this axis, I've put the input, proper units have to be given, of course, and on the other axis, we are plotting the output with proper units. So if we actually plot the output versus input, for a linear system, the plot is going to be a straight line which is passing through the origin, meaning that in this case, automatically your principle of superposition and principle of homogeneity would be holding good. On the other hand, for nonlinear systems, nonlinear systems do not obey the principles of homogeneity and superposition. So there are, of course, lots of examples of nonlinear systems, some of which you are already familiar with. So, say for example, there is a characteristic like this, that is a system which has the output to input characteristic, which is as shown over here in the red, color. So this is what we call a saturation, right? So you see that the response of the system, this is the output axis and this is the input axis, right? So as I'm varying the input, the output is proportionately varying. So basically, this portion of the plot is a straight line passing through the origin from here to there, right? But once the input exceeds, say, some value which is xs, it's mentioned as xs over here. So basically, if the input is greater than xs, what has happened? You see that the output no longer, increases. Say for xs, the output is some y1, not marked, but say this value is y1. Okay. So now if, instead of xs, I have something which is greater than xs, say the input is here, again, the value of the output is y1. And if I increase the input still further, say this is my input value, the output is still y1. So basically in this region, what has happened is saturation has taken place. So similarly over here, in this portion, saturation has taken place. So overall, this characteristic is known as a saturation characteristic, right? Also, there is another example which is given over here. The hysteresis loop that you have for, your electrical materials, you would see the characteristic is like this. So over here, the extension is plotted on this side, how much it extends, and the force being applied is plotted on this side, the other side. So basically, the characteristic shown is over here, right? Also, your BH loop also will be the same thing. There are, several elements which show hysteresis. Over here, of course, you can see the mechanical system plot has been shown, but the plot would be similar, not same, but similar. So here now what we see is that the output over here and the input is given. So the output to input plot follows a curved line like this, and not only that, the output is dependent on whether the input is increasing or decreasing. So when the input is increasing, say for example, if it follows this curve, when the input is decreasing, the curve will be following the other one. Okay, so you can see loading and unloading written over there. Loading means that the extension is keeping on increasing. That is, it's going to follow this plot for that condition. On the other hand, when unloading is occurring, meaning that the extension is being released, it's becoming smaller and smaller, this path that is labeled as unloading will be followed. So this characteristic now of the output versus input is not a straight line passing through the origin, meaning that for equal changes on this side, that is the input side, there will be unequal changes on the output side. So basically this also, the hysteresis also can be categorized as a nonlinearity. And whenever you have any element which by itself is nonlinear in nature in a system, the overall system becomes nonlinear. I'll repeat what I said. Let us say that there is, in your overall system, there is an element, say for example, you have an amplifier which has saturation, okay. So only that component has saturation, all the others are not, they have a property individually. If you look at it, they have a linear characteristic. But because of the presence of that amplifier with saturation within the system, the overall system would be called a nonlinear system, okay. Nevertheless, basically, you can see that for a nonlinear system, the characteristic will not be a straight line passing through the origin. Now, having said that, I would also like to point out some things which sometimes students tend to confuse. Over here, this characteristic on the left hand side that I've drawn, the straight line passing through the origin, just note the axis over here. The axis on this side, the axis is input, and the other side it is output. So this is not a time response that I've plotted, right? For a time response, I would have had time on this side and some, say the output on the other side. But this is not the time response, mind you. So a ramp input is not a linear system. Basically, that has no relation with this whatsoever, because for a linear characteristic, what we would have to plot is the output versus the input. So once I keep increasing the input, the output should be increasing proportionately, and if I decrease the input, the output should be decreasing proportionately. But this is not the plot of the output versus time, right? So don't confuse, right? Similarly, with the nonlinearity as well, the axes are input on this side and the output. So basically, these characteristics are the input-output or output-to-input characteristic, not the time response. So keep that in mind. It's obvious, but sometimes, students tend to confuse them. If you just have a ramp input, you say that, oh, it's a linear system. No, that's totally different, because that's a different plot on a different axis, right? But this is a linear characteristic for a linear system. So now, a question, that is, you have this plot, which is a straight line again, okay, and similarly this one, which is also showing, you can see that, okay, I don't know whether it's visible on your screens, hours of TV watched and grades. So grades is coming down proportionately, inversely proportional rather, with the hours of TV watched. But naturally now the question is obvious, meaning that first tell me about the left hand side, this characteristic. Is it a linear characteristic?
Ma'am,
Yes,
incrementally linear.
Bolu Arigba?
Non-linear.
The left hand side one?
Non-linear.
Non-linear, yes. Why non-linear?
Linear must be passed through the origin, and it must be a
Yes.
straight line.
Yes. Both are straight lines, mind you, but straight lines are not passing through the origin. So what will happen if I consider, say for example, the left hand side, this example as if I consider it, I can see that when the input is 0, the output it has a finite, quite a good value. So say for example, if the input is very, very small, say I have the input as 0.001, my output is, say for example, 10 over here, okay. Now if I increase from 0.001 to 0.002, I would be expecting that the output would be 20 then, but that is not going to happen for this, isn't it? Because the characteristic is not passing through the origin. Basically, it is a nonlinear characteristic. Similarly with the other one as well, though it is a straight line, but it's not passing through the origin. So basically, this is also a nonlinear characteristic. So both of these are nonlinear, though they are straight lines, but not passing through the origin, as a result of which your superposition and homogeneity will not be holding good. You can just take, algebraically considered the, I mean, or numerically, you can verify that. It's easy to verify. So now coming to another classification, that is, systems may be classified into continuous systems and discrete systems. So as far as continuous systems are concerned, now of course this is a plot versus time, mind you, this axis is time, right? So in a continuous system, the response or the output will be continuous, and the time side also is going to be continuous. So the domain, that is time, is going to be continuous, and the output is also going to be continuous, right? So I mean, in continuous systems are continuous in time and output domain. When I say that, what I mean is that corresponding to, say, for example, on this side, the time axis I'm considering, okay, so t equal to 4 seconds, okay, 4 seconds, 4.01 second, 4.02 second, all those I can get from this plot, and the corresponding value thereof, output value. So output value also is continuous. So each, I mean, you see that basically corresponding to each, I mean, time on this side, however infinitesimally small increase from the previous value, basically there would be a corresponding output, and the output also is, I mean, changing in a continuous fashion. So both the domains, that is the time domain and the output domain, are continuous in nature for a continuous system. On the other hand, as far as discrete system is concerned, discrete systems are, I mean, not continuous in two domains. There are two possibilities, I mean. So what are the two possibilities? One possibility is that the discretization is on the time domain. So time domain means what? Okay. This is a bigger plot of the same thing. So I'm showing you this one now. So basically discretization along the time domain means that I have a value corresponding to t equal to, say, 0, and then say 1 second, 2 second, 3 second, for example, okay, 4 second, 5 second, but I do not have any values intermediately. This plot actually is a bit sort of, it is a bit different. What has been done over here is, okay, I'll just exit from the full screen mode, and I'll try to put in a bit of, I'll just put in, say, small stars somewhere. Okay. Okay, that's big enough for me to. Let me say that at t equal to 1 second, the value is as shown by the star. Okay. Now at t equal to 2 second, the value is as shown by the second star, that is this one, right? Now at t equal to 3 seconds, say the value is this much, or rather, let me put it over here. Then let me say that, I'll just put the stars first. Actually, what happens is, usually I use the board in the class and draw this diagram on the board. So that is why I have to make a bit of a change so that you can understand what I'm trying to convey. In just a moment, okay? That should more or less suffice. Okay. So let me again present it. Right. So now what has happened is that for t equal to 1, I've put the value by using a star, right? T equal to 2, I've put the value by using a star. So you can see that between 1 second and 2 second, what is the value? You see that there is no value. That is the output I will not be able to get between 1 second and 2 second. Okay. So basically, the discretization is along the time domain. So if I mean, look at this, at t equal to, say, 1 2, 3, 4, 5, 6, etc. Or it could have been, I mean, not necessarily integer values, 1t, 2t, 3t, where t can be anything. So now what I mean to say is that the output is available only at discrete instance of time, but the output is not available intermediately. Forget about what was marked earlier. Basically, what was marked earlier is that the values were joined by using what we call a zero order hold. Zero order hold means what? Whatever previous value it had, it's going to hold on to that value. But nevertheless, that is not what I'm trying to say over here. So here in this particular system, the characteristic that you see, this is the output side and this is the time side. So now, I mean, say for example, this is what, how much? 1t, 2t, 3t, 4t, 5t. So this is 5t, this is 6t, right? So 5t, you have a value which is over here, right? You can read that. If the axis had a scale, you would have read that value. And for 6t again, the value is this much, right? So you can read that value. But how much is the value between 5t and 6t? You see that, say for example, I take it midway. The time over here is midway between 5t and 60 seconds. Okay. So here, let me see what happens. I cannot read the value. There is no output corresponding to that time, right? So such systems are called sample data systems, where the discretization is along the time domain, right? So, I mean, there will be no signals which you get at intermediate instance. So within the interval, you will not get any output. Only at discrete instance, you will get the output value, right? On the other hand, there is another category of systems which are also discrete in nature, but there the discretization is along the output domain, or rather what we call discretization along the along the event domain. So in that case, what happens is that the output can be either of, say for example, you can see an example over here. The output can either be pump on or pump off. There is actually nothing intermediate between those two, right? So discretization is not there along the time domain. Time is continuous. You can try to see what is, I mean, corresponding to every instant of time, what the output is, which is going to be, the output is either going to be the pump on or the pump off. So all digital systems fall into this category, where you can, I mean, have the output as either 0 or 1, or on or off, things like that, right? So basically, such systems are also, I mean, not continuous systems. So you can say that they are discrete systems. But in, I mean, within discrete systems, the two categories, that is sample data systems and digital systems, those systems, that is when the discretization is along the event domain or the output domain that we usually say, then in that case, the system would be categorized as a digital system. On the other hand, when the discretization is along the time domain, such systems would be called as sampled data systems. They are also discrete systems, meaning not continuous, but specifically they are in, I mean, the subcategory under which they fall is this, that is sample data systems, which is different from digital systems. So this actually was the classification of continuous systems versus discrete systems, right? As I mentioned, discretization along either the time domain, in which case it is going to be called sample data system, or along the event domain, in which case it is going to be called digital system. Next, we come to another categorization, which is called either time invariant system or time varying system. So now, within this category, you see, in a time invariant system, the parameters of the system remain constant over time, right? And in the time varying system, parameters of the system vary with time. So now, I mean, what would be termed as parameters of the system? Parameters are different from the signals in the system, right? So basically, I mean, say for example, if we have such a system, so the equation of a system of a circuit which has an inductance and a resistance is given by Vt equal to ITR plus L dit dt, right? This is the equation governing the system. So now we have to look at, I mean, if we want to categorize it as either time invariant or time varying, basically what do we have to look at? We have to look at the parameters of the system. Now in this, I mean, equation, which are, or rather in that system itself, what are the parameters of this system? Can you tell me? You can see several things, I, V, R and L. Which of those are considered as parameters of the system?
L and R.
Yes, very good. So L and R, because they are actually, these values would be coming from the components themselves, right? And basically the values would be known in certain terms. So basically R and L are the parameters of the system. So in this equation, if you look at, in the cursor is gone. If you look at this equation, you would see that the parameter R is not a time varying one, it's a constant. R means, capital R means it's constant, right? Similarly, L over here is not a function of time, so it is a constant. So from that point of view, this particular equation would be categorized as a time invariant equation, or rather it is the equation of a time invariant system, because the parameters R and L are constant. On the other hand, if we have an equation, a similar equation but not the same, the difference in this equation is that here, apart from the fact that V equal to IR plus LDI dt, and VT and IT are of course time varying signals, you have R, that is a parameter of the system, is a function of time by itself. Similarly, L, which is another parameter of the system, is also a function of time. So because R and L are time varying over here, this system is going to be called a time varying system. So basically, I mean, when you are going to categorize a system into a time varying and time invariant system, or time invariant system, the first thing you would have to do is you would have to identify the parameters. Which are the parameters? So now if I look at the parameters, are they functions of time or are they not functions of time? Are they constant? So in case they are constant, the overall system is a time invariant system. In case they are not constant, meaning if they are time varying, then the system is going to be called a time varying system. So unless you do that, basically just by looking at the equation, if you see, oh, I is varying with time, so it's time varying. No, I mean, I is not a parameter of the system. I and V are signals. So if you apply an input voltage, you are going to find that the signal, that is your current, is time varying. That is not a parameter of the system. On the other hand, R and L are parameters for this particular system. So I hope that is evident. So in any system, you would be able to categorize into time invariant and time varying systems. Yes, so RT and LT are time varying parameters in this second right hand side equation. Then coming to another categorization, which is that all systems may be classified either into lumped parameter or distributed parameter control systems. So as far as lumped parameters are concerned, you can see an example on the left hand side. Most of the systems that you usually handle would be lumped parameters, meaning that over here you can see that the resistance is clubbed together. It will have some value, R1 or R2 or whatever, and you have a source of power and the current is flowing through the circuit, right? Now in comparison, or in contrast to that, in a distributed parameter system, the parameters are going to be not, I mean, you will not be able to club the parameters together. The parameters would have to be distributed in space like this, right? So, I mean, you already have studied in your second years systems, which are power distribution lines, which have to be expressed somewhat like this, variations of this. So you have the resistance and the inductance, I mean, not concentrated at single points like this one, the left hand side one, but the same resistance, I mean, the overall resistance of the transmission line, that is the distribution line, if we want to express it properly, you would have to consider the resistance distributed just like this as shown over here, and that is going to continue infinitely, meaning that you would be able to model the overall distribution line with the help of infinite such inductors and resistors as shown, right? So such a system, the right hand side one, is called a distributed parameter control system. And of course, I mean, modeling as well as analyzing it is going to be different from when we have a lumped parameter control system. So those actually are, the categories, the broad categories under which control systems may be classified, right? So right now I'll start with another module. Maybe we will just start with it and continue in the next class, because I don't think there is time enough to finish this whole thing. It's quite a few, I mean, at least 1.5 lectures it's going to take. So now we are going to study about the steady state error and error constant. So basically till before this, we had the introduction part. Okay, so introduction to linear control systems ends over here before this slide. So now we are going to go to steady state errors and error constant. So now, what is steady state error, right? So the steady state error, you are already familiar with. In your second years, you would have plotted, I hope you have plotted rather in your signals and systems, the responses for very simple first and second order systems. And over there, you have seen that some systems for certain inputs, the response achieves the steady state value, right? So here now we are going to study about steady state error, and correspondingly something which is associated with steady state error, which is known as error constant. So steady state error is a measure of the accuracy of a system. By accuracy, we mean over here that if I apply a certain input, how closely that input is being followed by the output, right? So over here, basically you can see small diagrams, but some small plots, I mean. But here, the first one, that is the left hand side one, you find that the blue plot is the input which is being applied to a particular system, and the green plot, actually this one, signifies the output as a result of application of that input. Of course, for a general system, I'm not speaking about any specific control system over here for the time being. So now you find that the input was applied, the value was changed at the initial instant, and then it was constant at this particular value, whatever the value is, say unity or something, 1. So now, as a result of application of this input, we find that the response is like this. So in the response, you can identify a transient portion, which is over here, say, and from this point onwards, or maybe here, you find that the response, the output no longer changes. So it has reached the steady state value. So the difference between the input and the output is what we call the steady state error, which is the topic of discussion now. Similarly, in a system, if we apply a ramp input, the ramp, you can see, this is the input side, the signal side, I mean, and this is the time axis, right? So the signal is changing with time. This is the input signal, the blue one, right? Now the response is shown by the cyan, the magenta, I mean. So over here, you find that this one, that is the pink plot that you see over here, the magenta one is showing you the output of a general system. Okay. So here now in this system, or rather in this response, can we identify the steady state and the steady state, steady state error? The answer is yes, though this is a ramp input. Naturally, because it is a ramp input, the output would be expected to follow the ramp in the steady state. Now, there is a point or a particular time before which the response has variations like this. When I say variations, I mean the difference with respect to the input signal keeps on changing. On the other hand, there is a particular time, say for example over here or this one, after which the difference with the input signal remains constant. So here, basically in this portion, let us say, the response has actually reached the steady state, though it keeps on increasing, but the input by itself was increasing anyway. So basically here as well, we can identify the steady state error. That is the difference between the input and the output is remaining constant, and that value is called the steady state error. And of course, I mean, we have to wait till the transients are over and the response reaches steady state. By steady state, we do not mean constant value, but what we mean is following the input without any, I mean, the difference with the input rather remains the same thereafter. So now coming to what is written on the slide, the steady state error is the measure of the system accuracy. So over here for the second system as well, you can see I've applied a ramp and the ramp is being closely followed. Now how closely? You can say that, I mean, there is an appreciable level of accuracy in the output because it is trying to follow the input. However, there will be a steady state error. So this much will be quantifying how much of accurate, I mean, how much less accurate, or how much rather, how much error there is in the steady state response. Now this error, meaning the steady state error arising from the nature of the inputs, type of the system, from nonlinearities of the system components such as static friction, backlash, etc. So we will actually be seeing these meaning the definition of what type of the system means, etc. As we go by over here itself, we will be defining. But nevertheless, I mean, as far as this slide is concerned, the steady state error arises from, number one, the nature of the inputs as well as several other properties of the system. For example, the type of the system, nonlinear components which may be present in the system, etc. The steady state performance is usually judged by using some standard inputs to the system. Now, such standard inputs are the step input, ramp input, and parabolic inputs. So, when we look at the steady state performance of a system, we will be usually looking at the performance due to the application of a step input, or due to the application of a ramp input, or a parabolic input. So these are three inputs, which are taken as standard inputs, by application of which we look at the steady state performance of the system. There are, of course, other inputs possible. Say, for example, if I put a sinusoidal input to the system, yes, I can do that. But as far as steady state performance is concerned, it is not the, I mean, conventional thing to judge the steady state performance by applying a sinusoidal input, or for that matter, any other input apart from these three standard inputs. The concept of steady state error and error constants is valid only for stable systems. So only when a system is stable. For stable systems, the concept of steady state error as well as error constants is valid. I mean, no wonder, because I mean, in an unstable system anyway, in an unstable system, your response is going to be, changing with time, though your input may be constant. So, I mean, a constant, or maybe if a step input is applied, your output will have an oscillations which are increasing in magnitude, etc. So basically, in that case, there will be no question of attaining the steady state, and hence the concept of steady state errors will, I mean, be sort of not relevant in the first place, right? So the concept of steady state errors and error constants is valid only for stable systems. Okay, so yes, the small plots that we were showing are actually, I mean, drawn over here in a sort of magnified manner. You can see that the steady state error has been marked over here as the difference between the input signal over here, this one, blue one, which is a step input for this particular diagram plot, and the output, which you can see has transients, but after that it reaches the steady state. In fact, I should have labeled the steady state a bit later as well, but anyway, after the steady state is reached, the difference with the input signal is termed as the steady state error. Similarly, for systems in which the input signals are time varying, like this one, so you find that this is the ramp input to a system, that is the blue one, and the corresponding output has been shown. I cannot take the steady state error from this here. Say for t equal to 3 seconds, if I say that the value is this much and that's the steady state error, it will not be correct, because we can see that in this portion from here to, approximately this over here, you can see that there the difference between the input and the output is changing. But after a particular time, say for example, for this particular plot after 8.5 seconds or something like that, after that we find that the two plots, the input and the output, run parallelly, which means that basically steady state has been reached. So now the difference with the input will be termed as the steady state error of the system for that particular input. So this would actually be the last things that I would be saying today. So the three standard inputs which are applied to systems are basically the step input, ramp input, and parabolic input. So as far as the step input is concerned, step input is of course different from a ramp and parabolic, of course. But what I wanted to say is the step input is different from a constant input. What is the difference between a constant input and a step input? You are familiar with the step input. That's why I'm asking. You have done it in your second years again. So what is the difference between a step input and say, if I say I'm applying a constant input, what is the difference? What would be the difference?
Step input is 0 below for negative time.
Yes. So step input, actually for a step input, the step input is applied at a particular instant. For this case over here at t equal to 0, the step has been applied. So it means that before t equal to 0, the value was at a different level. Say if the input value was equal to 0, and at t equal to 0, the value changed from 0 to a different value, say k over here as marked, right? So basically for a step input, there is an instant when the the signal changes from one level to another level, right? So for our ease, or I mean for sort of for simplicity rather, usually we say that that happens as t equal to 0. T equal to 0 means what? T equal to 0 is something that we have labeled as the time from which we are trying to study the response, right? Because t equal to 0 is not the time when the universe started, isn't it? So I mean t equal to 0 actually, I mean in absolute terms means nothing, but if you want to study a system and those study the response, and you start from a particular instant, you label that instant equal to 0. So what we are saying over here is at t equal to 0, meaning at that particular instant, we are applying the step input. So before that instant, the value was at a previous level. Say for example, it was at 0 value, then it just changed suddenly from 0 value to k, and then remained k thereafter. On the other hand, for a constant, as you have correctly said, for a, if I say I have given a constant input would have remained at the same value, whether wherever the t equal to 0 is. So I mean the signal does not change level at any instant, not even the t equal to 0. So I mean if I would have seen beyond this, before this rather, I would have seen that the input was still held at a constant value for a constant input, but for that's not valid for a step input. Now, of course, ramp input is shown over here. You can see you are familiar with this as well, and then a parabolic input where the variation is of it's following the nature of a parabola, so t squared, something constant into t squared, it's going to vary as. Now, basically, there are two questions on this slide. One of which is that which of these signals, that is the step, ramp, and parabolic, is the most severe? By severe, try to. It's a bit vague as far as the terming is, the terminology is concerned. It's, there's nothing as, you can call it more severe or less severe. But what I'm trying to say is that, say for example, somebody told you, okay, you have your system now. I'll give you only one signal as the input. Which signal are you choosing to apply? Now, common sense would say that, if I really want to test what is happening in a system, I would be applying the worst possible signal. Worst possible means the signal which was most likely to affect the response in an adverse way, right? Or rather, at least, when you study stability, etc., you will see that, basically, whenever you apply a signal, the objective would be to check whether the response is sort of meeting performance criterion by application of that input. So, in general, we would be wanting to use a signal which would test the performance to a greater extent compared to the other signals. So now, can anybody try to answer the first question that is given over here? That is, which amongst these signals, that is the step or the ramp or the parabolic, is the most severe?
Ma'am, the parabolic input.
Why?
Ma'am, because as time progresses, the input increases more. I mean, in a rather greater way, in greater amount than the step input or the ramp input. Step input remains constant for as time progresses.
Okay, I've heard your answer. Anybody else who disagrees and has a different answer? So everybody agrees with what he has said? Unfortunately, the answer is not correct. Does anybody want to sort of make an intelligent guess regarding what it could be and why, of course? Okay, I'll tell you the answer. Basically, in the step input, you find that at t equal to 0, there is a step change. Step change means there is a jump from a previous value to a different value at this initial instant, right? On the other hand, in the ramp input, you find that the input is gradually varying with time. It's proportionately varying with time. The parabolic input as well, initially the change in the input is small, and then as time progresses it keeps on rising. So there is, in the ramp input and the parabolic input, the jump, that is sort of a single instant when a change in the value is taking place, is not present in case of a ramp or a parabolic input, isn't it? Do you agree with me? Because over here in the step input, you find that at a particular instant, the value changes from a previous value, say for example, 0 value, to a different value, which is say k, but that change happens almost instantaneously. And when I say almost instantaneously, you know that practically, of course, something happening in 0 time is almost impossible. So naturally, it's going to be within a very, very small time interval from say t equal to 0 minus to t equal to 0 plus, where t equal to 0 minus, it was equal to some other value, say 0 value, and t equal to 0 plus, it came to k. Do you agree with that, or disagree with that?
Yes, ma'am, it's okay.
So basically, of these three, basically, if we apply, so you would see that in fact, whenever you are analyzing control system, people say, okay, apply a step input and show me the response. The reason is this, that is, if you apply the step input, it would more or less take care of a lot of things. Basically, you would be able to analyze it to a sort of greater extent, or rather, many things will be exposed if there are possibilities of the performance criteria not being met, etc. They will be exposed if I apply the step input. Now the second question before I wind up today, that is this, that is, now you can say that, ma'am, the impulse input, if I apply, impulse means what? It's not drawn over here, but at a particular instance, say at t equal to 0, I have a value which is very large, and then again it goes to 0, right? So the next question is that, is the impulse input more severe than the step input? I'm asking with respect to the step input, because of these three, understood that the step is the worst one, right? So now comparison of the impulse input with the step input. Which one would be more severe? Why?
Is it impulse?
Why?
Because in an impulse, there is a sudden increase in the voltage, and also there is a sudden decrease at the same time.
Okay.
So system has to respond very quickly to that kind of a signal.
Okay, but what about the step? In the step, doesn't that change occur?
After a step has only one time when the signal increases, at that time step has a sharp change.
Okay.
But after that it remains constant.
Okay.
In
So,
impulse, we get 0 to infinite at a sudden period,
mhm.
and also from infinite to 0. But in step, we get 0 to a finite value, and that's why I can
Okay,
say
infinite
impulse
is after all going to be finite. It can be large, but practically, I mean, what do you mean by infinite? It's going to be very large, fine. But then after that, what is happening in the impulse? The impulse, I mean, your signal is being withdrawn, isn't it?
Yes, ma'am.
On the other hand, in the step, I am applying at a single instant and then keeping the input. What I mean is that, first of all, regarding that infinite value, yes, I mean, theoretically, you can have, I mean, if you want to compare, I can have a very large step value and also the impulse value may be large. So, I mean, as far as the magnitude is concerned, if I take of the same magnitude, say, magnitude means that if I consider an impulse which has a very large value means what? Okay, 1000 volts, 80,000 volts, something like that. Okay, so I mean, now if I want to compare, if I put the same value of input, I mean step input. So in those two cases, that is going to be some finite value, isn't it? Not, I mean, infinite means very large. So basically now, I mean, the comparison is between the fact that in the impulse, after application at the initial instant, the input is withdrawn. But in the step input, after application at the initial instant, of course, instantaneously, we still keep on applying the same input at the constant value. So, I mean, if say, for example, I sort of try to bring an analogy between, say, if you are standing somewhere and somebody gives you a push and then withdraws. Okay, withdraws means just gives you one push at a particular instant, you fall, fine. Okay, so that is one case. That would be the case of an impulse, right? So gives you a push and then doesn't push you any further, right? So that is the case of an impulse. On the other hand, in case of a step, the person is giving you a push at a particular instant and then keeping on pushing you, not withdrawing the force, isn't it? So basically, in the step, the signal is kept on, I mean, it holds the previous value. Once the initial instant is over, the signal is still applied. So, I mean, basically, if say, for example, you think about the case of an electrical system where some voltage is applied and then withdrawn, or it's applied and voltage source is kept connected. So basically, I mean, you would be able to see what would be the changes in case not only the I mean initial instant, that is at when the sudden change takes place, but when a constant is being applied. On the other hand, if the signal is withdrawn, what would happen is that you are able to find out what happens when you apply and then forget about it. Forget about it means it's no longer applied, so the signal is cut off, right? So that is the difference between these two inputs. So in my opinion, or in general, the step input would be a more likely choice in case, I mean, you are given a choice to study a system by application of an impulse input or a step input, right? because impulse, I mean, of course, the concept of infinity is something that you, I mean, are having in mind, that is accepted and understood. But when I say infinity, I mean, if I'm applying it in a physical system, I would actually mean some finite value, isn't it? And then that value is withdrawn. The forcing function is withdrawn. On the other hand, over here, it is applied at a particular instance. Sudden change does take place, but after that, we again keep it applied. So that is the difference between the step and the impulse. And from that point of view, you would, I mean, understand that basically, compared to the impulse, in the step, you still keep on applying the same input, right? So, I mean, if somebody is applying a force, the force is still being applied. The constant force of, say, some 10 newtons you are applying somewhere. So, it's being applied. On the other hand, if you had an impulse, okay, initially you had 10 newtons, but then 0 newtons. So, basically, it's no longer being applied. So, anyway, these are qualitatively, I mean, I mean, to just to understand, to feel, I mean, which one would be better, which one would be worse. I have, I mean, sort of initiated this discussion. Now, as far as the steady state errors and error constants are concerned, these are the three inputs which are going to be used, and by means of using these, the errors will be studied and calculated, and the error constants also will be defined. But not today, because we are going to actually require one whole class for that. So I'll end there. Today I'll stop the recording and the presentation, but I'll take your attendances. Don't leave before I take your attendance.